Flame fundamentals. Professor Maruta is a professor from Tohoku University and the deputy director of the Innovative Energy Research Center and Institute of Fluid Sciences in Tohoku in Japan. He's a very well-renowned scientist in the combustion community, having done lots of work in experimental combustion, microcombustion, combustion under microgravity conditions, and also studying combustion for high exergy efficiency technologies. I'm reminded of many of his past works on microcombustor applications. You can read many of his papers, being one of the world leaders in microcombustion. Also now working more recently, I've learned in lean burn engines and turbulence and chemistry interactions in these types of engines. Professor Maruta is well known in the Combustion Institute community. He's been on the editorial board for most of our major combustion journals, also an active member in the proceedings in the Combustion Symposium, which is held every 2 years. So we welcome Professor Maruta for these lectures, and we hear he also has lots of interesting hobbies, one of them being he is an excellent singer. So don't expect that he will sing, but you can be expected that he'll put on a good performance for you all in terms of the lectures. And remember, make sure you ask questions. He's going to be happy to give the microphone for whoever will ask the questions. Professor Maruta.
Thanks, Manny. Okay, good afternoon, everyone. All. First of all, I would like to thank the professors from KAUST, colleagues, Professor Roberts, Professor Dibo, and Professor Im, and also Professor Sarti, Manny, maybe, yes, to give this fantastic opportunities to me. Actually, I have been sending my students to the summer school in China. It is the Tsinghua Princeton summer school. And I have been jealous to my students because those are very nice ones. I really want to attend. And this is my first time to attend the CA summer school. So I have been very excited to be here to share with this opportunity. And it is the very first day that I would like to give you an intuitive images of how the flame fundamentals. And since I'm an experimentalist, I wouldn't go to the details of those theories, but I will show you some of the fundamental phenomena, including some videos and then stuff. And we have 4 hours from now, and then I have like 3 parts of this lecture. So I'm planning to have the break 2 times. Since there's no clock, if I continue to talk more than 1 hour, please stop me anyway 1 time. And then take 1 break, maybe. Okay, anyway. Again, my name is Kaoru Maruta from Japan. And I'm in the Tohoku University. So let me just quickly go through how the Tohoku University is. Our university locates in the city called Sendai. Sendai is on the mainland of Japan. It's 300 kilometers north of Tokyo. And city is very compact and called the city of trees with lots of greens and stuff. Those images, that image from our headquarters here. And our university is around 110 years old, founded in 1907. And we have mission statements, 3 mission statements. Research first, open doors, and practice-oriented research and education. And you will see those 4 pictures. I think it's almost 100 years, but some of the very familiar stuff for you would be from our university. One example is this is the direction antenna, which is called the Yagi antenna, which is very widely used in the world. And also, this stuff is the hypermagnetron, which is also used in all the microwave stuff. And then this is a perpendicular magnetorecorder, which is this principle is used all in the hard disk that maybe you're using, and also the optical fibers here. And myself, I say that it is 25 years since I started the career as a combustion researcher. And then in 90s, mainly I have been dedicated to combustion under microgravity. Actually, 3M, microgravity combustion, and this is mild combustion, and this is microcombustion. So I'm always saying that 3M, microgravity, mild, and microcombustion. And let me make acknowledgements to my collaborators, particularly those three people. Takashi Niyoka, Professor Takashi Niyoka, a former boss. He is already retired. He has been in the UC San Diego, working together with the Professor Williams, and of course that he has a lot of theoretical papers. I'm not. And also I met Professor Igwan Ju. Now he's working in Princeton. Actually, he got a PhD in Tohoku. When he was a student in Tohoku, I was at the sort of postdocs, which is called Research Associate, and we worked together. It's really exciting period, and then still that sometimes we met and then we talk, miscellaneous things. And one more, the one guy from Russia, Professor Sergei Minev. Now he's in the Far East. I've been collaborating with him for 20 years. He's fully the theory guy. So he's working on pencil and paper. And basically, I'm experimental guy. So I always look at what the theory indicates, theory imply. And also other guys, former postdocs, who made a lot of contribution to microcombustion work. And my current colleague, Dr. Nakamura, and Professor Komari, a former postdoc, also contribution to the microcombustion, and two technical staff who made all the experiments successful. And also together with the other researchers, postdocs, and students. Okay, let me start the contents. So my lecture consists of 3 parts. One is basics, and second, flammability limits, and third is the flames under extreme conditions. Of course, many extreme conditions, but it's not a comprehensive view. I just talk a couple of them mainly from my experiments. So, in the first part, basics consists of the sort of introductory remark and SCurve, premix, non-premix, and flame characteristics. And at the beginning, I heard that 1/3 of you are not a combustion researcher or combustion engineers, just working in a mechanical engineering field outside of combustion. And 2/3 of you are working on combustion. So it's a bit hard to cover such a big diversity of the audience. So I will try my best anyway, okay? Okay, from introduction. So flame classification is always at the beginning of the textbook. I think most of you are very familiar with that. You know this one? Of course, this one. Do you know this one? Guess what? Correct, microgravity. Droplet combustion. This is the flame from stove. I took this picture in my home. This is also candle flame in microgravity. And I think this is also microgravity, but this is common outwardly propagating flame. So flame is classified like premixed, non-premixed, depends on how the reactants are prepared. It is mixed, then premixed. It's not, then non-premixed. Also, depends on the flow conditions, laminar flame, turbulent flame, of course. And then this is the flame image from jet. If it is fully premixed, then image becomes like this. This is premix flame. And then if you just eject the fuel flow only, then flame length is elongated and many sooty lesions. And intermediate, just mixing ratio is sort of continuously different. So it's obvious that the fuel rate, flow rate is same. So the premixed flame has small, which means that reaction, overall reaction is fast. Again, stabilized and propagating flames. This is a Bunsen flame, as you know, and the flame is just stationary. It is because that flame is balancing with local flow. And important thing is that premixed flame has a nature to eat up the fresh mixture. And this speed is unique. And if you ignite in the mixture in the container, then flame is usually propagating outwardly. So the same flame, but motion to the frame is different. And the flow is laminar. This is laminar flame. And this is the Schreiner image which visualize the density change. So weakly turbulent flame, and this is sort of the stronger turbulent flame. Those images are from my thesis. I think it's 30 years ago. So practical combustion, always with turbulent flame. So the upper one, reciprocating engines. And middle is the gas turbine engines. And the bottom is like furnace, incinerator, like the combustion, which uses the heat itself. So our goal, combustion researchers, engineers' goal is to understand and to predict the phenomena in those systems and also try to improve those systems. And this morning I talked with the young guy who's working on engine. Sometimes that combustion theory does not work because maybe the engine is too complex. But still, under the principle of basic combustion theory. Okay. Let's look at the history of the combustion research and also the scientific and technological developments in the world. Starting from very long ago, like 100 and 150 years. Just take a look at it. Steam engine, manned flight, Ford, and World War II. And this is the start of the computer investment, supercomputing, and here, periodic table, and here, the concept of electron, atom, molecule, those stuffs. And right-hand side is the combustion research. So study on combustion limit has been started very long ago in terms of the safety in mines. And mostly that empirical data is very important to avoid the explosion in mines. And then after that, without computer, just imagine if you time slip to that period and you are the combustion researcher, but no computer. How do you explore? How do you clarify what happened in flame? The answer is mathematics. Based on the governing equations, the renowned professors like Professor Williams, Zeldovich, they are dealing with the governing equations. But the difficult part is the exponential term, reaction term. So to obtain the analytical solution, it has a very specific technique, which is called, for example, asymptotic analysis. And Roshan group use like a delta function, because it is always true when the activation energy is very large. And then trying to capture the big picture of flame, how flame behave. So the before computational period, the combustion research mostly divided into two: experiments and math. So comparison between two. And then after computation, as you know, with the progress of the computation performance of the computers, the more and more things can be solved. So much more realistic, from quantitative to qualitative to quantitative computations ongoing. And also that nowadays, so many researchers are working on chemistry, kinetics part. Now, I think so combustion theory is sort of the old stuff, regarded as old stuff, but sometimes it's really, really useful. And then nowadays, quantum chemistry of initial and stuff. With these process, it's the history of the seeking for the very ideal flame, because now it's readily available that you have Chemicin or Cantera or stuff. And I heard that all of the KAUST students are using Flame Cloud. It's from Cantera. Okay, so, and then if you type the conditions, then you can have readily available that you have the flame speed, adiabatic flame temperature, everything. But guess, time slip to 50, 60 years ago. How you can do that? So I believe that the use of combustion. I think this morning that Professor Dibble mentioned that application first. So the combustion research made significant progress, ironically, because of the war. And after the theoretical combustion, mass, and then computation, kinetics, and trying to seek the ideal flame. And then look at that. This is the first International Combustion Symposium, the Combustion Institute. That's actually before the war. And then west side and east side are separated for some time. And then after that, I think after the war, that they start. And I'm gonna talk later. The world's first microgravity experiment was done. Actually, that scientific experiments in microgravity was on combustion, and also by Japanese professor from University of Tokyo. And microgravity experiments contribute very much on understanding flame fundamentals. Because of the lack of gravity, we can have very stable flame. We can avoid some of the very unstable nature of the flame. Okay, let me go on. SCurve. Actually, SCurve is named that because it looks like S. Here it's like maximum temperature, flame temperature, or whatever, like m dot. And here is the Damkela number, which is defined by the flow resistance time divided by chemical time. I think concept is very, very easy. Assume that you have the candle. You light it, and then it's stable combustion. What's happened here? Of course, some complicated phenomena ongoing on candle, but chemical reaction occurs at a certain time, not infinitely fast, some finite time. But overall flow resistance time allows the chemical reaction to stay there. So how do you extinct the candle flame? Yes. This makes the flow resistance time shorter than the chemical time. That's why flame blow out. This is a very, very simple concept, but all applicable to the burner flame, also counterflow flame. I think it's even supersonic combustion overall. So if your frame is unstable, then either increase the chemical reaction speed or reduce or increase the flow resistance time. Then the phenomena is going to right side of the figure. So this is stable solution which correspond to flame. And if you decrease somehow the reaction speed, then Damkela number becomes smaller, 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 and finally the flame extinct to this is the like ambient temperature, the stop reaction. On the contrary, that if you put ignition source or something, and then if chemical reaction speed is faster than resistance time, then ignition occur. And then flame states to this. So this is the so-called SCurve. On the other hand, that it is called Fendel curve. So this concept is very convenient to roughly consider the phenomena and also intuitive recognition of the phenomena. What is the important? What's happened here? And I believe I heard that some of you are from chemical engineering area. Who's from the chemical engineering? Yes, okay. So this is CSTL, I believe it is continuous start tank reactor, is it right? This is a reactor which has inlet and outlet. So reactants are coming in. After rapid mixing, reaction occur, and then flowing out after a certain time. So you can define the resistance time here, also chemical time, so which can tell that by the SCurve. And similar to the chemical reactor, we can define, as I mentioned, that ignition and stable combustion and extinction from this idea. So from the analogy between the combustion reactor, I think you can classify very roughly. The batch reactor, this is the, like for high school student physics piston and cylinder model. But this is exactly the engine model without any port. Of course, engine, and also shock tube also. Rapid compression machine, it's same batch system. On the other hand, CSTL, if you extend the definition, it's Bunsen flame, candle, turbulent flame, also some flow reactor, gas turbine, it is the CSTL system. And combustion problem is really widely multi-scale. So chemical time is the like 10 to minus 2 or even longer. For example, it's no NO formation. This morning that Professor Dibu mentioned that NO reaction is very long. So how to manage the NOx stuff? 1970s, 60s, 70s, it is the biggest issue in the world to avoid the air pollution. So what the combustion device do is that using this difference of time scale. So NO formation is very slow. So in the equilibrium conditions, NO formed in a certain amount, but since the reaction speed is very low, chemical time is very long. So after extracting the energy from combustion, which is usually the very high speed of combustion, chemical reactions, and then just stop the formation of NOx. That's the main strategy that modern combustion devices are doing. And this is, 10 to minus 4. This is the product formation, H2O. This is sort of main combustion. Radical formation. And depends on radicals. The speed is very different. Like H2O2, it is very fast. And physical time is within a certain range. Commonly, the physical time range is smaller than the chemical time. The flow time, turbulence, modern devices, I think flow time is less than this scale. And transport, molecular transport, turbulent transport, and also radiation transfer is important, is much faster. And if you're working on DNS, you need to have the 10 to minus 10 or even faster time scale should be handled in your model. Because some of the chemical reactions are very fast. This is the comparison with the ethylene combustion and heptane combustion. I think it's detailed would be given to the later lecture, but in some of the like alkane reactions, some reactions are very fast, even at the 10 to minus 12 second order. So the distribution is different. So if you fully tackle with the N-heptane reactions in DNS, the time step should be very short. Okay, again, please imagine that all the chemical kinetics are unknown. You need to have like a standard phenomena to construct the reliable chemistry kinetics. So for that, mostly on ignition phenomena, I think representative method is the shock tube. I believe that, have you looked at the, students looked at the shock tube here already or not yet? Already. Yes, and some of you are working on that maybe. And also rapid compression machines. I think this is the same style as that you have here, right? This is the style of the twin piston style from Ireland, Galway. Professor Henry Callan's group. Very reliable data is obtained. So then, if you have standard experimental data and some of the theoretical work combined together, and then you have the reliable chemistry. Also for ideal flames. What is ideal flames? So it is obviously that probably one-dimensional. also adiabatic, also without any external effects, which means that the area is infinitely large, perfect plane, and propagate into only one direction's plane. Have you ever seen that plane? Never, because flame is unconditionally unstable, so it's difficult to observe ideal plane flame. So as I mentioned, that before computational era, maybe more directly, when the chemicin was developed, the most important thing is that having the ideal frame, which can be a standard of the development. So, do you know this flame? Someone know this flame? Actually, this is the frame that I will mention later. It is very similar to the counterflow flame, but this flame is the stabilized in front of the polar cylinder. And this is the counterflow flame, which has two nozzles. In this case, one from one fuel flow, another from the oxidizer flow, to have completely flat flame. Okay, flat, but the flow effect, flow is diverging. This effect is remained. Twin flames, same as this, but you have the two premixture flow. So this flame is symmetry to this center plane, stagnation plane, and then flame structure, temperature, everything is symmetrical to this plane. This is propagating flame, totally spherical. If the radius is large enough, the curvature effect can be negligible, and the flame can be regarded as the plane flame. Same as droplet combustion. How about the Bunsen flame, which is common? It's ideal flame. It's difficult to say to be ideal because of some effect. Curvature, and also flame is always touching the burner rib, which is suffering from the heat loss. So burner becomes hot, right? You cannot touch after a long time. This means that a certain amount of heat is escaping from flame to the burner. This means flame is under the effect of heat loss, which is not ideal condition. And how about this flat flame? Also, this is difficult because flame is there because flame is thermally trapped by the porous. So upstream, some heat transfer exists. This means that you need to compensate this effect. So I think it's the easiest starting point is the homogeneous reactor 0D model, which is, I think it's some of you are using daily, who are working on the shock tube data, LCM data. LCM data also, you should have the heat loss term and with the other compensation pressure term. But originated in, for example, if one interested in understanding this, it's very easy. I think it's available in the internet. It is, I think it's, now this word is not used in chemichin, but originally it is senkin. I think it's in Aurora package. I've never used Cantera, so I don't know. Okay, after maybe too easy introduction for you, let's go to the Premix Flame. This is Bunsen flame. This flame is stable because flow and flame propagation speed is balanced. But if you decrease the mixture flow rate a little, then flame length becomes shorter and shorter, and then finally that flame going back to the tube. And still, flame is trying to go to the upstream. But there should be a one point, ideally, there should be a one point that which can balance flow, speed, and local propagation speed balance. And then this flame is stationary, but relative to the mixture, flame is propagating to the mixture. On the contrary, that if you increase the speed, this is blow off. So from Bunsen flame, we have several very basic flame characteristics here: laminar burning velocity, flame quench, extinction, blow off, flame structure stuff. So I believe most of you are already familiar with the chemical modeling stuff. And for the premixture, the mathematical treatment is sometimes starting from the Rankine-Gurney relations, because there are two mores, which is the faster than the sound speed, and also much smaller than the sound speed. One detonation and another deflagration. So flame is actually that deflagration, and several levels of the mathematical treatment possible. Actually, I borrowed these physics figures from the combustion physics. In this simplest model, flame is treated as just a discontinuous interface between unburned and burned gas. And both sides are thermodynamically equilibrium. This concept is very often used when the structure of flame is not important. And second level is here. Although the reaction sheet, flame is treated as infinitely thin, but other factors, transport in preheat zone, is considered. And also mass and heat diffusion occur in that zone. So some of the reaction zone thickness appeared here. And if Lewis number, which is the ratio of the mass diffusivity to the thermal diffusivity, can be assumed as 1, this reactant concentration and temperature distribution should be a mirror image, which will lead to the very simple governing equation. And third one is realistic, that I think it's in chemical stuff. All of you are working on this zone. Here, that reaction zone appeared, that you can discuss about something on the intermediates in them. So reaction zone thickness and this transport, convective diffusive zone thickness, all. And then if you want to predict the laminar burning velocity correctly, definitely that you need to have such very precise model. But depends on the purpose. You can switch one model to another. Those are the well-known set of the governing equations for premix, 1D ideal flame. But to model that, you needed to have the ideal flame. But nowadays it's possible because highly reliable kinetics are readily available, and also other thermodynamic model, transport models available, so you can compute the flame speed. As you know, that this is one of the very, very basic, very old mechanism mainly for methane combustion, GRI, developed in Berkeley. And then here, you have the species, and from here down this is continued. Each elemental reactions are described. Even in this simple case, that more than 300 reactions are considered. And then this is a very rough example of the methane oxidation. Starting from methane, if the first model, I mean just reactants turned into the product, then you can only consider methane and CO2. But if you need to consider the intermediate and also the process of the reaction, you need to have some species. Believe that, for example, Zeldovich presented just a two-step models. So before the computational period, the overall one-step program, overall one-step reaction has been used, still used. But once you need to consider the behavior of the intermediates, any intermediates, radicals or much heavy molecules, whatever, then you need to have another intermediate species. Also, this predicts something very useful. So this is sort of realistic, and main route C1 path is from methane to CH3, CH2O, HCO, CO, and CO2. And now the very detailed discussions along the CH3O path, CH3OO path, some very modern kinetic work based on the free, theoretically, it's predicted. And then now the methane kinetics are going to the perfect stage. Laminar burning velocity, so laminar or rather laminar burning flux, because the low SL is the much easier to compare, for example, in the different pressure conditions, that at normal atmosphere, the flame speed like somehow slightly below 40 centimeters. And with increase of pressure, the laminar flame speed decrease. But laminar burning flux, if you consider the density, then it's increased because the reaction mass rate is increasing. And then before coming, I tried to compute the iCloud flame. Is that right? iCloud flame. And this is by Chemikin, and you can readily compute very nice chemical structure. But if you are the newcomer of the combustion research, if you just compute it, and then, okay, understood. But what do you understand? Of course, computer made output of the nice, fancy chemical results, but what can be understood from that? So rather than the such very nice, fancy model, the very, very old model is sometimes somehow intuitive. So this is the very, very old model from 1880s. The flame is regarded as two zones, zone 1, and the also reaction zone. And then just equate the flow going to the reaction zone is equate with the reaction rate, and then you will get the laminar burning velocity is this dependence, and then readily available that you can have the relation between flame thickness, laminar burning velocity, and thermal conductivity. This is sort of easier to have the intuitive understanding. For example, we have the methane flame with air, but if you replace nitrogen with other inert, then flame speed changes drastically. For example, if you replace nitrogen with argon, the flame speed increases. By helium, even more. How do you explain? If you have Chemikin, of course you can compute it, and then you have the right answer. But why? So here, for example, argon flame is faster in laminar burning velocity. Why? because the argon is monatomic gas. So the specific heat is lower than nitrogen. And heat release is same because fuel amount is same. So the temperature, flame temperature of argon flame is higher. And if you compare with argon and helium, both are monatomic gas, so then flame temperature should be almost equal. But thermal diffusivity of helium is much larger. So the laminar burning velocity of helium case is much larger. So something like that. It's slightly easier to capture the physics inside. And starting from the governing equations in Chemichin, further simplifications were done. And then went to the very, very simple one. Such activity was made like Zeldovich, Williams, Claban before computational period, particularly for Zeldovich case. It is like 1940. And one who are interested in such the derivation process, I think I strongly recommend to read the book of Dr. Thierry Poinceau. It is one by one, the very process, all the process was described in that book. Actually, that I learned that his summer school lecture in Princeton is very, very good, and I borrowed 4 slides from his lecture. Okay, so a bit different, but this is like a set of the equation, same as the Chemichin and stuff. And then you have the result if you have the code and the computer. But simplification is made by assuming that you only have the 2 reactants, fuel and oxidizer. But if you assume that fuel linkage, then majority of oxygen just remained without affected, so that you can ignore the change of the oxygen concentration. Then you only need to handle the fuel concentration. So only one reaction for the deficient species in reactants. And then you have the very simple equation, which can be solved by hand, that Dr. Poinceau said. And this is the field of the actually theoretical combustion. So usually that they initialize the fuel concentration by initial concentration. So in the system, the non-dimensionalized fuel concentration is between 0 and 1. So initially, that fuel concentration was 1, and then consumed fully, and then becomes 0. On the other hand, temperature, starting from the room temperature, and this is adiabatic flame temperature, and then if non-dimensionalized, also that flame temperature becomes 0 to 1. And then 2 equations can be 1 if Lewis number, mass diffusivity and thermal diffusivity is equal, then combine into 1. And this theta, non-dimensional temperature and non-dimensional fuel concentration, the sum is 1 everywhere, which means that chemical enthalpy, which is carried from the mixture, can be turned into the thermal energy. This is just a chemical energy is converted into temperature. And then you have the very simple equations, convective term, conduction term, also reaction term, and then only one variable left. And then this can be regarded as the reaction progress variable. So only one parameters you can describe the flame property. Okay. Based on that very, very simple idea, also you can treat some of the very typical flame behavior, like flame quench, flammability limit, and quenching diameter, or excess enthalpy combustion, flaming survey, that stuff. And then those topics would relate to the mild combustion and microcombustion. Actually, this is the very natural constellation. It's like a game to imagine one to another between simple flame to very typical phenomena. Okay, so ideal flame. By the way, what's the time? Oh, it's already 1 hour. As I mentioned, ideal flame is hard to realize. Always heat loss may affect flame. Also, flow non-uniformity, and some wall effect, either thermal or chemical or both. Because of that, you need to be very, very careful to prepare ideal flame or flame with a certain effect. And then laminar burning velocity should be measured very carefully by considering those external factors. So this is the data of the laminar burning velocity as a function of equivalence ratio taken from the textbook in Japan, published in 2001. So numbers are the devices. Of course, this is review data. Numbers are from what type of the device have been used to measure it. It's obvious that you can look at that for example, the highest laminar burning velocity is attained slightly richer side of the stoichiometry, and how is the deviation? I think it's nearly 20% difference. It's 2,000. Still 20% difference. What's wrong? And very interesting data, much more comprehensive data, can be seen from the paper by Professor Igor Fopoulos from USC. This is the review paper from PEX. And then in 1950, the deviation of the laminar burning velocity. Oh, this is the highest maximum laminar burning velocity of methane air mixture at standard conditions from the fabrication. Now it is almost converged, like slightly larger than 35 centimeters per second. What was wrong? One is stretch rate, right? What others? Okay, I will talk this one by one. Of course, it's not one by one on the data. So let me briefly go through the very basic methods of measuring the laminar burning velocity: burner, flood flame, propagating flame, control flame stuff. So this is the burner method. The laminar burning velocity can be measured from the inclined angle of the nozzle. It is possible, but for high fidelity modeling validation, I think it's difficult to use this method, I believe. And the flat flame method stabilized only above the flat flame burner. But why flame is there? If flame is free from any heat loss, flame can be here or wherever, right? Why there? Because of some heat loss, stabilized flame just above the burner. This is very modern flat flame burner, which has developed in the Eindhoven group, Professor De Goy group. It is very clever way. So they have like a porous plate with the temperature measurement by thermocouple. And if you magnify this part, the porous plate, the heat balance is like this. So this is the heat from flame to the porous, and then this porous is heated up. But this heat, again, heat the incoming mixture here and here. So that if you measure the temperature history, time history of the porous media, then you can find a point that all the heat loss effect can be canceled. So then you can measure the very precise measurement of laminar burning velocity. Very special technique. And how about counterflow? So counterflow flame is very commonly used. Variety of the studies have been done by using this flame. So this is, again, the one-dimensional. Although that fuel is diverging, there's no conductive heat loss because flame does not touch to the burner wall. And the flow could be characterized by a unique parameter, which is a stretch rate. So flame stretch is very important. And how do you measure the laminar burning velocity? By this. This is the actual velocity distribution, this part, magnified. And then here is the stagnation plane. So because of the expansion, that this velocity profile has a minimum. And then this point tells the laminar burning velocity soon before the flame. When the flame is under the stretch rate, the flame behaves in different manner with increasing stretch. When the Lewis number, which is defined, the thermal diffusivity divided by mass diffusivity, then if you increase the stretch rate, then flame temperature once increase and then decrease before extinction. If it is neutral, then nothing happens. But if the Lewis number is larger than 1, just with the increase of stretch, flame temperature just decrease and then lead to extinction. This is because here, across the flow tube, the mass and thermal transports are not balanced. Sometimes flame is intensified, and sometimes flame are weakened. This affects very much to change the very different behavior. This is, and then from that minimum point, this is under a certain rate of flame stretch. And then if you plot this velocity as a function of the stretch rate, then you will extrapolate data, and then you will get the laminar burning velocity, which is free from any stretch effect. Again, outwardly propagating spherical flame. This is one of the ideal flame. Mixture in the container, and then ignite at the center, and then propagation. At the very initial stage, the laminar burning velocity was tried to be measured from the pressure history, together with experimental data and some simple analysis. But this makes very big uncertainties. And then, of course, that some of the other factors are included. Again, flame stretch, because ideally, it seems like that this assumption works well, but sometimes the flame stretch, ignition energy, other factors affect very much. So it's interesting to see the history of the measuring of the laminar burning velocity by using this flame. Since the concept of flame stretch, studies are progressed, I think it's the late 70 to 80, so before the concept of flame stretch. Always this effect is hidden in the scattered laminar burning velocity. That's the reason that many of the results are suffered from the flame stretch effect. Okay, so since the flame stretches are important, let's confirm that the definition. Definition is the the change of the frame area, unit frame area, divided by the unit time, and some equation derivation leads to this equation. This equation represents that the effect of flow in non-uniformity and like flame curvature. You can divide into this one. This process is also described in the very nicely in this paper. Professor Chan and Lo, and Professor Chan is the, as you know, that the founding director of the CCRC. And let's confirm that in stagnation flow, the stretch rate is equal to the velocity gradient here. And spherically expanding flame, or this term, this here should be plus. The change of the radius and radius itself, you can describe the frame stretch rate. So based on this stretch rate, you can have the plot as a function of stretch rate, and then again extrapolate to the stretch-free condition, and then you can have the laminar burning velocity in D and in Rich conditions. This is really basic, but if you consider the Lewis number, it is interesting to see some of the interesting behaviors. This analysis is, I think it's 2000, this is 11, but first papers, I think it's 2007. And some of the French people started analyzing such process. But from ignition to the propagation, where is the boundary of the ignition phenomena and flame propagation phenomena? It's not that so simple, because for example, for building the kinetics, you are talking about the ignition in 0D system. So this is spatially uniform. This condition is somehow realized by shock tube and also by maybe rapid compression machine. But usually that ignition started from one ignition source. So starting from point, and then propagate. And then after some time, the reaction front can be regarded as the flame. So this process is totally different, depends on Lewis number. So this is the normalized flame radius, normalized by flame thickness, and this is the normalized by the flame speed at adiabatic conditions. If Lewis number is smaller than 1, then ignition kernel growth is very rapid, and the speed easily exceeds its ultimate value, which is, this is laminar burning velocity, which is free from the very small curvature. The flame can be plane, regarded as a plane flame, but propagation speed is larger once. But with the increase, the Lewis number, the behavior is different. And for example, if the Lewis number case 0.2, for example, practical fuels like gasolines, always Lewis number is larger than 2. So in such case, if you consider the ignition energy, then with very small ignition energy, actually Q is ignition energy, then once you ignite, the flame just die. Start reaction, but not going to the flame. But if you increase the ignition energy, then with increasing, then somehow the in parameters of the ignition energy is large enough, then it's in green line, or maybe pink line, which leads to the flame solution. But here, you have valley of the curve. So this behavior is well characterized by very, very simple theory first, and then computation with kinetics, and then again, also experiments. So which means that, for example, that in Lewis number larger than 1, then local speed is once becomes very low, and then again going back again. And also, here this theory implies that this point, a turning point, the solution is only stable upper of this point. So below that point, there's no realistic physical solution. So you need to reach anyway. For example, if in the case of Lewis number 2, you need to reach this point. This is the so-called critical frame radius, which you need to get there to make a smooth shift from ignition to propagation. So this is the very nice data I borrowed also from the Princeton Summer School by Professor Igwanju. So ignition start, and then when initial, then flame speed becomes very low, and then again recover, and then going to asymptote, to the real value. And this is reported as a function of stretch rate. Then starting from ignition, regime 1, regime 2, and regime 3. The previous figure image, which is extrapolate, is only this part. Actually, that this theory and this tells everything from the initial ignition point to the laminar burning conditions. For example, the hydrogen-oxygen system is very, very simple and have been studied very, very long. But even the laminar burning velocity of hydrogen-oxygen mixtures at up to the very high pressures could not be measured because the lack of that understanding of those shifts from the ignition kernel to the flame. So after the recognition, and then very nice data is obtained and by the Princeton group. Professor, now he's Professor Mike Bach, I think it's, yes. And then it's really, well-cited data. So long history, but if large uncertainty, then maybe some hidden physics. So maybe you can find. So okay, and then I will briefly touch non-premix flame. Okay, maybe I'm running out. What's the, okay. Need break? Okay. I think it's, okay, so then let's have one break, maybe 10 minutes. What time is it? Maybe 2:25? We'll start again. Okay, thank you. So those pictures are example of the non-premix flame candles in microgravity, droplet in microgravity. And what's the force? Yes, okay. And also that non-premix flame treatment of the theory. So situation is like this, because fuel and oxidizer is transported to the reaction zone from different zone, and then if the reaction occur in the reaction zone and the reaction rate is finite. Of course, it's always finite, but cannot be regarded as infinitely fast. Then there is some reaction zone thickness here. And then in extreme case, there's some leakage of both reactants and oxidizer. This is realistic condition, but it is often regarded as that reaction is infinitely fast. And then reaction zone is just regarded as sheet, and no leakage is observed. So some of the commercial fluid dynamics code uses such assumption, but we need always to be very careful about the limit of the applicability of such model. It's counterflow non-premix flame. And this is the very conventional oxidizer from top and then fuel from bottom. And here is the, I think it's the similar to the conventional counterflow flame, but it is, flame is formed just in front of the polar cylinder in the stagnation region. And same research is possible. And actually this effort has been done by the Japanese professor, Professor Tsuji. So this burner is called Tsuji burner. This is very original, and I think no one criticized that this data taken this burner contributed significantly to the establishment of the very high fidelity modern flame modeling, like chemical and stuff. And by using Tsuji burner, I think this work is in late 60 to early 70. Actually, they probe temperature, and also they probe the very thin quartz sampler, and then measured the species concentration profiles. So here's temperature profile. Here, I think this is the surface of the Tsuji burner, cylindrical surface zone. Here's the luminous flame zone. So temperature is highest and then decreasing. And, fuel consumed, some of the intermediate, and also oxygen diffused from bottom, and then react, some leakage observed, and also products here, and some intermediates here. And it has been famous that in Japanese students that there's no line in the data. They made lines by the data points. So it's very reliable experiment. And for the young researchers, now Combustion Institute announced the Hiroshi Tsuji Early Career Research Award. So this is sort of the gold medal for the young researchers. And this award is named after the contribution of Professor Tsuji and also Tsuji burner. So please try to get it.
Bill has a question.
Yes.
Yeah, how old do you have to be?
I think it's the younger than 60.
Oh.
No, I'm joking.
I give this back to you.
Okay, sure. Actually, the 10 years since the PhD degree. So the ones who is less than the 10 years from your PhD, then try to get it. I think now there's only one winner. And then this year, I think it's the second winner would be announced. Okay, regarding droplet combustion. Droplet combustion is the fundamental study of the spray combustion. Of course, spray is spray, but the simplest component is the single droplet. And experimental work in ideal condition actually was done in 1950s in the dropping apparatus like this. And then the very famous D-square law, reduction of the droplet size with burning, was characterized by this experiment by the Professor Kumagai. Actually, this is the first scientific experiment conducted under microgravity. And then I heard that this is the trigger to start all kinds of experimental work under microgravity. This is 1950, and this is very recent. This droplet combustion experiment was done in International Space Station. I think it's the This is read by the Professor Foreman Williams from UC San Diego. And by using this, the free droplet is formed in microgravity and very ideal conditions. No buoyant flow, no objects along droplet, and then such very nice image obtained. I think I will distribute the PDF files of this, and I recommend you to take a look at those YouTube stuff, because very, very nice image and very nice announcement of the results was there. Okay, let's go for the flame characteristics. This includes flame quench, flammability limit, and quenching diameter, and excess enthalpy combustion, flame instability. Let me very quickly go through this. Okay. This is the basic theory of flame quench, which is actually that initially presented by Dr. Zolovich in 1940. And then Dr. Spalding, and Clavan, and Williams, and then so stuff. Okay, let's look at this image. This is the temperature distribution of the very ideal adiabatic one-dimensional planar flame without any external effect. So temperature is uniform here in the burned gas side. This we call adiabatic flame. But once a certain kind of heat loss exists, or body loss exists, whether it is uniform or local, then heat is escaped from here. And since heat generation occurs in the reaction zone, typically temperature distribution becomes like this, some gradient. This means the flame is under the effect of heat loss. So this occasion is described by the very simple, well, this is just one energy equation, same as the one that I mentioned in the very simple one, but with one parameter, which is related to heat loss, L. In this case, maybe uniform, which is the proportional to the temperature difference. And after some deformation of the equations, you have the heat loss parameters L. And then if you plot the non-dimensional burning parameters, which is normalized by the adiabatic flame speed, then when the heat loss is 0, now this is adiabatic flame, laminar burning velocity. And then, but if you increase the heat loss, then the value of the laminar burning velocity is decreasing, and also have two values at a certain heat loss parameter. So based on the stability analysis, this upper branch is stable, and lower branch is unstable. So physically, this branch does not tell anything. And then finally, at this point, beyond this point, if you increase the heat loss parameter, there are no solutions there. So this is the extinction point. So this is like conceptual indication that if you increase the heat loss parameter, then flame extinct. So thermal extinction occur. And then this is the laminar burning velocity as a function of equivalence ratio, which is always appeared in the combustion textbook. It has the maximum close to the stoichiometry, and value is different from fuels. Hydrogen is such, and then C2 species higher. But what's happened in the both sides, here and here? Lines stopped. Why? Anyone who?
Who's going to answer it?
It's too much fuel and too much oxidizer on both sides.
Yes, of course, yes, you're right. But if you extend it, then you will have a value of the so-called flammability limit. So some of the combustion handbook, it is written that for methane air mixture, what's the limit, concentration, something like that. But many, many complicated phenomena occur on that region, so that the curves are stopped over there. So this right figure is presented 1950s. Based on the analysis of thermal quench, this is actually the publication by Dr. Spaulding, and this is the curve that you see in your textbook. And he divided into several cases, and then see if the heat loss is not effective, close to limit, then curve should be like that. So which means that flammability limit should be 0% fuel. Because if you have a small amount of fuel, then it should react. Is it correct? Okay, which one is correct? Guess which one? Someone? It's not easy to answer, right? It's a question more than 50 years ago, but still, it's difficult to answer. And if you have a limit with a certain kind of heat loss, then curve becomes like this. It's like this, the shape like the Japanese rice bowl. And if you look at this curve, and this is, for example, if this concentration, this is the upper solution, and this dashed line here corresponds to the lower curve. So the curves are now closed because of heat loss. So which is correct? And this will be discussed in the part 2 at flammability limit. And then quenching diameter. So I think most of you know that if you put the flame in the very thin channel, like quartz channel, then flame would die because, who knows? Yes, heat loss too much, yes, that's easy. But same, right? Same discussion based on the thermal theory. Just heat loss is replaced by the conduction heat loss to the channel instead of unknown. So the same discussion is possible. Excess enthalpy combustion. Actually, this is the fantastic idea. This is the Weinberg. Is Weinberg fine now? I met him a couple of years ago. Weinberg is fine.
He passed away 5 years ago.
Oh, 5 years ago, okay. Actually, this is the paper appeared in Nature in early 1970. Okay, this is sort of conceptual figure. This is adiabatic flame temperature. But what's happened if that thermal energy that burned gas has is transferred to the unburned mixture? What's happened? That's the question. Then, of course, I think it's the configurations are not correct, but by heat transfer, temperature increase. And then reaction starts here. And then highest temperature is much, much higher than the adiabatic flame temperature. Is it great or nothing? Temperature is value, right? If you remember the thermodynamics, if you have higher temperature, this is a higher value. But if you bring the same fuel, if you burn adiabatic flame, then the temperature is decided, right? Adiabatic flame temperature. But if you circulate only heat energy, then you have the higher value temperature, which may lead to the higher efficiency of the system. So this is sort of very big, innovative idea, which was attained by such configuration. Look at that, only one inlet and only one outlet. So you have the one pass, bend to U shape, and then roll, so that the burned gas high temperature can be effectively transferred to the incoming temperature, incoming mixture. And this is the geometry. And conceptually, this is the figure. This is adiabatic flame case. And this is, red one is when the heat from burned gas is somehow transferred to here. Then reaction occurs here, and then higher temperature obtained. So this is the concept of excess enthalpy combustion. And this will be discussed in part 3. And then let me just quickly stop by the flame instability. So flame is not always plain. Very often suffered from some of the unstable nature. This is the picture, very nice picture from the Professor Low's textbook again. And if you take a look at very carefully, for example, in those two left column is for hydrogen air mixture, expanding flame. And when same pressure, if it is lean, then the surface is all corrugated and then under the big instability. But if you go to the rich case, flame is smooth. It is sort of ideal flame. Under the same pressure, if you go to the propane, it's vice versa. When lean case, flame is smooth. And when it's rich case, flame is under the instability. This can be interpreted through the diffusive thermal mode instability. Actually, that in the theory, some of the diagram which predict the boundary of stability and also different stability mode. It is well written. It is written in the textbook and papers. But furthermore, those are 5 atom data also here. When fuel-rich case, hydrogen used to be stable at 5 atom, but if you go to 20 atom, the flame, again, under the very strong instability. Same happens in propane. If you go to 20 atom, it used to be stable in lean condition, but it's not anymore. So flames are under the several instability mechanisms, mainly for the body force instability, diffusive thermal instability, hydrodynamic instability. So these two and these two are interpreted like diffusive thermal instability, but at higher pressure, hydrodynamic instability would be the mechanism of the occurrence of the instability. Those are very famous figures. This is the explanation of diffusive thermal instability. Across the flow tube, because of the different diffusivity, the light species are diffusing across the flow tube, coming in and out. Vice versa, then mass diffusion can compensate or cannot compensate. So such preferential diffusion makes the diffusive thermal instability. And hydrodynamic instability is due to the expansion. So once the plane flame is perturbed, and then once perturbed, then this instability is just encouraged. So the flame is unconditionally unstable in terms of hydrodynamic instability. And so many theoretical works are conducted. And this is also important, but in practical case, I have a question to the expert audience. In engine combustion, is there any discussion on the hydrodynamic instability? Who are working on engine combustion?
I would say the higher, I'm going to actually cover this subject tomorrow a little bit more, but I would say these effects are wiped out, kind of is overwhelmed by the turbulence effects.
Mm.
And that's a general kind of a consensus about modeling turbulent combustion, and which is why a lot of time people often neglect the preferential diffusion effects in the model.
How's the onset on the knocking?
Onset
The knocking?
onset of knocking has to do with the
Flame stabilization. Question, maybe.
Onset of knocking has to do with the auto-ignition phenomena,
In some case, of course.
right?
But regarding some of the mechanism from DDT, then, for example, the Shibashinsky-Kagan discussed the flame complication parameters tells DDT, and also maybe applicable to the engine condition. I don't know, but just I really look forward to having your lecture. From tomorrow, I'll be a student. Okay. This is end of part 1. So can I just switch to the part 2? Okay. Can I do it now? Okay. Part 2. Okay, part 2 is for flammability limit that we just discussed. And I will tell briefly about history as shown here. Counterflow flames, flame ball, and a project that I have been working on, the comprehensive combustion limit. Okay, so the study on the combustion limit or flammability limit have been twofold. So as I mentioned at the very beginning of the talk, safety in coal mines, and basic limit theory was just presented for you. Thermal limit, applicable or not. Anyway, we have very, very simple theory. And then tremendous amount of experiments have been done. And then I think it's up to year 2000, the limit mechanism of the plain flame are almost clarified. I think it's with the contribution of the microgravity experiment. On the other hand, some peculiar phenomena called flame ball was predicted and observed and confirmed. I will tell you later. And then now we are going to unify those two to comprehensive understanding. Again, this is the simple theory. Okay. Flammability limit may be induced by a certain heat loss. If loss is effective, close to limit, then the flame can quench. So is it due to conduction loss, radiation loss, adiabatic? Guess what? What is the mechanism of the limit defining mechanism? Some papers, because radiation is proportional to 10, T is power of 4. So should be effective at the higher flame temperature. But examination on for example, the flames close to the stoichiometry show that radiation is not significant. How about the close to the limit? That's a question. Again, same thing. So the Spalding theory, very simple theory, imply that if thermal loss exists, curve is like that. It's not like that. Okay, many experiments using constant volume chamber, also the propagation tube. It's very early work for fire safety. The US Bureau of Mines define the standard to measure the flammability limit. This is the tube with the, like this diameter, 5 centimeter diameter, and long, this long, and then check the flammability limit. And then, sorry that this is very small, but if the flame is propagate, I cannot, upward, the limit concentration is somehow between 4 to 5% mixture, but downward mixture, it's 8, 9. What's that? Some data can be seen. If you incline the tube, the limit is function of angle. Why? For the case of methane, it's not bad like hydrogen, but still insufficient. Upward case, it's some 5%. Downward case, 5, 6%. But if you look at the flame is totally deformed. So it's not ideal flame. So what's the relation between the configuration of the flame and the limit? The big question. In the combustion chamber, the so-called SEF, self-extinguishing flame, has been observed. If you ignite the mixture, and then flames start to ignite outwardly, but at some radius, flame just disappear. This is called SEF, and this experiment cannot be done under the gravity field because the gravity just break away all the flames. But if you make the experiment under gravity, under microgravity, the SEF is observed here. So at that time, that it was inferred that some of the thermal balance and also the effect of curvature that we have discussed in the flame stretch has been combined effect. So here is the history of the flame radius with time. Here, SEF observed. So flame propagate, but disappear at some condition. But in different conditions, flame just completely consume. Okay, of course, other method is counterflow flames, which our group employed. If you employed the counterflow flame configuration, that external factors, heat loss, buoyancy, wall effect, curvature can be avoided, but only flame stretch remained. And then if you make the experiment by keeping the constant flame stretch rate by decreasing the fuel concentration, then you have the extinction points. If you repeat all of those experiments by changing the stretch rate, then you have such curve. And if you extrapolate this, then you will have the limit without any external effect. Such experiments has been conducted in the microgravity environment provided by the 10 seconds drop tower experiment. Unfortunately, the facility was closed like 15 years ago, but during the 5 meters free fall, we could have the 10-second microgravity conditions. And the users can occupy 1 meter cube in the 2 meter diameter capsule and then make experiment for 10 seconds. And I'm going to show you the image of the counterflow flame. The nozzle diameter is 3 centimeters. Then during this experiment, flow rate is kept constant, and then fuel concentration is decreased gradually. And then since the laminar burning velocity decreased, the flame is going to end going. And then at the moment of extinction, flame just disappeared. Whole part is disappeared. And then if you consider just a delay with the mixture, then you can identify the extinction concentration, and then you have hold the data. After this experiment, we got this curve. So the equivalence ratio, extinction here, and then flame stretch rate is here. For the propane mixture, the very straightforward curve, which would extrapolate to the limit, because in the textbook, those values are indicated. But for the methane case, the sublimit mixture is flammable, and went back to this value. So what happened? Actually, this is the computational work which tries to produce the methane case on the same plane. Of course, the different appearance, but equivalence ratio and stretch rate. This is equivalent to the flame stretch rate. So this is like C-shaped curve. And then for short, this is the temperature curve around here. So this means if you have the third axis here, temperature axis, and then plot it as a function of stretch rate here, then this is the curve. So you have the extinction here, and then also here, it is at this side. And then if you go to the Richter conditions, this upper island-shaped curve break up and then has some bifurcation occur. And then in certain conditions, there are two conditions are seen. So this means that for the same mixture, the flame can be two status. One is the higher temperature and another is the lower temperature. Okay, let me go through one by one. Okay. Here, if you plot the stretch rate here and then flame temperature, if you don't include the loss term based on radiation, then you will get this curve, which is identical to the curve that I showed before. But once you increase the radiation loss in the governing equation, then you would have another extinction point here. So this curve becomes 2 with 2 extinction points. And if you look at the radiation fraction, which means that if you estimate the total radiative loss with total domain divided by the total heat generation, then with the decrease of stretch rate, which means less and less chemical enthalpy is coming in the system, but the effect of radiation becomes increasing, and finally close to the extinction. It is very large. So because of that, in addition to this point, that in the lower side of the stretch rate, another extinction limit appeared. This is so-called the radiation extinction. And then this island shape consists the C-shaped curve, but further increase of the equivalence ratio leads to the bifurcation. And then this bifurcation, if you plot the flame standing off distance, then two flames. One is far apart flame, another is flame standing very nearby. So one is here, standing nearby, and then far from here. Okay, counterflow flame, far apart each other. What is this? This is actually the single flame. And at a very low stretch rate, the effective stretch rate is very, very small, which is asymptote to the adiabatic, no, not adiabatic, sorry, one-dimensional plane flame, but under the radiation effect. If the conceptual temperature distribution is drawn here, if the two flames are close, only small dip here. If there's no radiation, it's flat. But since radiation, it has some temperature dip. If flame is far apart, then radiation here. So then this frame can be regarded asymptote, at least asymptote, to the one-dimensional flame. So which means that leg of the curve is equivalent to the 1D limit. Okay, then if you change the Lewis number, for methane air mixture, Lewis number is like 0.97. It is almost equal to 1. In this case, the curve is C-shaped, and then this leg is here. So the sublimit mixture can be flammable up to this point, but 1D limit is here. So from this, we learned that we need to define the flame configuration when we discuss the flammability limit. So for safety, maybe we need to consider the widest flame geometry. And with the change of the Lewis number, for example, smaller Lewis number, which means, for example, the hydrogen-air mixture, or heavier fuels, much larger, then curve deformed like this. And then relation between turning point and planar limit is taken over here, around here, and then here. In addition to the very, very straightforward simple curve, such lower branch remain. So what we observed for propane air frame is this shape, and for methane frame, this she was observed. So eventually, the interpretation is like this. So this methane air curve, flame is interpreted like this, and the propane curve is like this. So sometimes limit of planar flame is not equal to the widest limit of the mixture. So this is the understanding of the limit, flammability limit of the premixed deflagration wave. Okay, let's go to the flame ball. Someone knows flame ball? Who are familiar with flame ball? Not so popular. Okay, so let me tell you a bit. Okay, flame ball is flame which does not propagate. So if you ignite the mixture, premixture, usually that from the ignition point, outwardly spherical flame is expanding. But the flame ball is just keep its radius constant and stay there, but only in microgravity. In the gravity field, of course, it's swept away by the buoyancy. And this phenomena was actually predicted theoretically by Zerdovich in 1940s. He's just playing around the equations and then found that, okay, just neglect term and only diffusion term and then reaction term balance, the spherical solution should be appeared. But after the stability analysis, he found that this solution was unstable. So this means that he concluded that this phenomena is not realistic, just a mathematical imagination. And in the adiabatic case, so this is actually the system is spherical geometry, and then this F is the heat loss term. So for simplicity, just because of the simplicity, just F equals 0 because it's adiabatic. And then it's very easy to have solution here. And then this is the solution. Inside of the ball, temperature is flat, and no reactant, no fuel there. Outside of the ball, the temperature may be easier to hear. So concentration of fuel is decreasing proportional to the 1 over radius. So it's very long tail, not like Premix Flame, very long. Sometimes the system scale, like 10 meters, even 100 meters, affect the results. And then for the temperature curve, yes, here. And then, I mixed up with temperature and concentration. This is the concentration of the reactant. And then this is like a mirror image. Actually, the phenomena was observed. I think it's 40, 50 years later than the Zeldovich prediction. Professor Loney from USC, when he was young, he made an experiment in the NASA Glen, actually, at Ohio, at the 30 meters drop tower, 2.2 seconds microgravity. He found something very funny phenomena. And then later on, that some mathematical cell addition experts analyzed those phenomena, and then guess it might be a flame ball, which was predicted very long ago. And then Ronnie and us collaborate, and then we made an experiment in Japanese drop tower and try to have the phenomena. And then after successful indication that Professor Loney made an experiment in space shuttle, I think it's his apparatus flight 3 times, and finally he proved the existence of stable flame ball. Why? Because the Zeldovich did not consider anything about radiation. But once the radiation term is introduced, like spotting theory, the curve, simple curve becomes bent, and then there has 2 solutions. So then another solution, another branch appeared, which might be stable. Why radiation term is significant close to the limit? This is because of the diffusion effect. Because of the diffusion, the reaction zone thickness is very large. Since temperature is very small, at least much, much lower than the stoichiometric combustion, radiation intensity itself is weaker. But because of the flame thickening, reaction zone thickening by the diffusion effect, the body effect is significant. And then finally, that rate of radiation divided by the total heat generation becomes large at very close to limit. That's a mechanism that radiation plays a dominant role very close to the limit. I'm going to show some video images. I hope this works. This is the experiment in airplane in the United States that Professor Loney did.
The existence of flame cylinders, evolving from and returning to flame balls or hot spherically shaped products.
Unfortunately, because of the quality of G is not stable because of the airplane experiment, it's difficult to conclude now whether the flame ball is stable or not. So then we made an experiment in drop tower in Japan. It's only 10 seconds. The end of microgravity. So it seems to be stable. So the flame behaves exactly that equation predict for the case of flame ball, also for the counter for flame. Once you introduce the radiation term and then just compute, then of course there's some complicated curve, but the frame just follows the prediction of governing equations. After that, through those experiences, I was so impressed that frame is always unstable and unpredictable. But once, if we prepare the very well-defined conditions, frame behaves as predicted. Okay. Also, I borrowed some images from Professor Roney's homepage. I think it's not available anymore. This is the experiment from the space shuttle. It's 15 years ago. For me, it's recent, but for you guys, it's long ago.
This now live video from inside the combustion module looking at the flame balls that Payload Commander Mike Anderson has ignited.
And bad for CM2. This is a tough one. We think we got a whole control room full of flame balls here, so we're going to call this the Orbit 2 flame ball crowd.
We copy, Dave. We can get all those flame balls named in the mission summary that we send up.
Okay, the lead flame ball is named Kelly, though.
Obviously.
Okay.
And Mission Specialist David Brown continuing the tradition to name some of the flame balls inside the combustion module, naming it after the Orbit Team 2.
They announced that during the 5 minutes, the flame is completely stable. Of course, it's not perfectly stable because after maybe 1 hour, 2 hours, then I think all the fuels in the container may be consumed totally. But so maybe we should say quasi-steady. But if the domain is infinite, then it should be stable. So then finally, the stability of flame balls were proved by the space experiment. Okay, what's the region of the stability of those flame balls? Let's look at this for hydrogen-air mixture. This is small percent of hydrogen, and the flame ball existence is like less than 4%, which is 3 point something. And if you convert it into the equivalence ratio, it is, I think it's equivalence ratio 0.1 something. And this is the very similar numerical experiments conducted for hydrogen-air mixture under the counterflow geometry. So again, like this sort of G-shaped curve, which has extended limit, turning point limit, relative to the plane frame limit. And then this line is equal to this line. So this means beyond the 1D limit, the flame ball solution exists. So this means in all the combustion textbook, the flammability limit of hydrogen-air mixture is this value, which means not the plane flame limit. But for fuels, which is larger than methane, it is always written that planar flame limit. Because in methane case, since Lewis number is 0.97, and critical Lewis number, which is where turning point and then 1D limit is coincide, is Lewis number around 1.25. So this means the methane case, the Lewis number is slightly below that, which means that extended limit has appeared in the counterflow flame. So the flame with low Lewis number is trying to survive, making the configuration change to have the curvature and then sustain under the lean condition. That's the mechanism. So again, when we discuss the flammability limit, we need to consider how is the configuration of the flame. Another factor is that the different heat balance. So if you have the mixture which has radiatively participating media, for example, in CO2, CO, or maybe methane, before combustion, if you have such species in it, then radiation emitted from burned gas is reabsorbed in the unburned gas. This might be the case at engine combustion in highly diluted by the exhaust gas. So in ideal condition, probably the limit is somehow affected by such effect. but no work there. Also, that by making the very large amount of EGL, the Lewis number of the mixture is different. So which means that different Lewis number effect, frame stretch effect, which is unknown. So under the very lean conditions, anyway, frame is sustained, seemingly beyond the limit. This can be explained by the different heat balance. So no fundamental work was conducted there. So the engine is choosing the very optimal point where that frame can survive. That's we can guess from those results. Okay, so far we have discussed the limit of plane flame and also limit of flame ball. But how is the combined effect? Actually, let me just quickly go through the project that we have been working on, past already 8 years. Now we are making the experiment in the airplane, and then I think hopefully we would make experiment in space within coming 2 or 3 years. The concept is the same, very simple. Flame ball can be observed in the quiescent mixture, but it is difficult to observe both deflagration wave and flame ball in the same system. Because of that, those two phenomena cannot be correlated. So by using the counterflow flame, but particularly very, very low speed, then condition is very close to the quiescent mixture, although some very weak stretch remained. So then maybe we can observe the flame ball in such geometry. And then, thanks to the well-characterized chemistry and modeling, preliminary computations made for counterflow geometry, of course, with radiation term, and also for the flame ball conditions, of course, with radiation term. And then results showed that, okay, we used a very artificial mixture. Instead of nitrogen, we are using krypton and xenon because those are heavy. So makes the Lewis number very small. And then SCurve responses are here for krypton flame and xenon flame. And then also computed predicted flame ball diameters are here. Okay, by the way, that flame speed, laminar burning velocity, is an eigenvalue of the governing equation of the 1D flame. And flame radius is the governing equation of the flame ball, because it is the constant value. So the flame ball limit of krypton mixture is here, and xenon mixture is here. Then if we combine those two into one, of course, in the different axis, as a function of equivalence ratio, the flame radius is here for flame ball, and stretch rate here. So then this means that this curve indicates that within this range, the deflagration wave is flammable. But below that, in this zone, up to here, flame ball should exist. So then if we start experiment here and then go close this curve, then we should observe the flame ball. That's the assumption. And then we have very small airplane in Japan for microgravity experiments. I think it's for 6 persons originally, and then make experiments. Very simple, same way, computer-controlled counterflow burner, and then by keeping the flow rate constant, the equivalence ratio is changed with time. And then this is an image of the experiment. Okay, in the airplane, some of the acceleration before microgravity, and then start going up, and then from here, the parabolic flight starts, And for about 20 seconds, the airplane experienced the free motion. So during that period, that we can make the microgravity experiments. Now it's 2G. I think our colleagues, once the microgravity starts, then they float because of the spring of the sheet. But with sheet belt, they stay there. Something happened. That's a very bad operation. Maybe data in that flight cannot be used. Yes. 2G, 0G, 2G. Who wanna do that? I did once. I was okay, but not anymore. We repeat the experiment like within 1 hour, as much as you can. So usually we do like 14, 15 times. Not my job. Okay, through this experiment, actually we did the counterflow flow experiment at very, very low stretch rate, and then look what's happened. So this is Krypton case, the twin flames. And then with the decrease of the stretch rate, flame becomes 1, and then instead of disappearance, flame is somehow trying to go back. Not perfectly spherical, but both. It's not that flashy image, but can you imagine how happy we are to see this image for the first time? This is very evident. Even in the counterflow field, that something like flame ball can be formed. Those line images, the some couple. It's just by accident it is coming into the. So this is not fully successful experiment, but image is good for the demonstration. Okay. Okay. Our interpretation. So this is the, of course, numerical constellation. Counterflow flame with the decrease of the equivalence ratio, temperature becomes lower and lower, and then extinct here. But at the same time, in the same mixture, flame ball solution has increasing temperature with decreasing equivalence ratio because the flame radius becomes smaller and smaller. And if you remember the governing equation of flame ball, it is a strong function of the radius. So temperature increase to the extinction. So then what we suppose is with decrease of the contour from temperature becomes here, but at this point, flame solution disappear. So then mixture trying to find the solution that flame can be. Then jump occurred to here, and then up to here. That's what I guess, we guess. I don't know the truth. Maybe we need to make further experiment. Yes?
Then jump occurs. What do you mean? The temperature climbs out of nowhere? There you are, 1200 Kelvin, and then you jump up to 1300 Kelvin?
Yes. So the counterflow flame was acting like ignition source of the flame ball. So mixture is ready to have any solution. But since the solution for the deflagration wave disappeared, and there's a thermal energy to ignite something, then flame ball is there. That's our interpretation. Of course, we don't know. Any other interpretation?
I have none.
Thank you. And then in addition to that, we found the phenomena like that. I hope the video works correctly. 8-year-old computer. Not smooth. But do you remember that the cellular frame image that I showed you at the flame instability? So initially, that counterflow frame is suffering from the instability effect. So flame is, nothing turbulent, but very stable laminar flame. But because of the flame nature, the flame shows the cell nature. Oh, does it work? Maybe, okay. And then we also made the three-dimensional computational experiment by using so-called thermal diffusive model, which does not solve the flow because the system dimension is too big to make the computation with detailed chemistry. So we obtain the overall one-step chemistry, and at a fixed flow of the counterflow field, we just compute. And then we found something similar to experiments. So flame, of course, further down there, we have flat flame, but at a certain conditions, flames start wrinkled because of the diffusive thermal instability. And then furthermore, if you decrease the intensify the radiation loss or whatever, and then those cells are separated into something like ball. Okay, this implies that we need to modify the whole picture of this image, mainly in those two areas. Here, we have the scattered ball image, which we named the sporadic frame. And also here, the frame, counterflow frame, cannot be plane anymore. The frame itself is trying to survive by themselves. So this is the regime diagram by the numerical experiment, and then compare with, of course, it's not correct. It's not quantitative, but qualitatively, that similar phenomena observed. So in addition to the she and also with leg, where we call G-curve, we have some of the extension by those ball-like frames, and also here we have cellular flame here. And experimentally, it is difficult to make the total survey in the airplane, but it is somehow close to the observed results. And how is the flame structure? Also, this is the numerical experiment by using diffusive thermal model for the sporadic frame and also common planar counterflow frame, and also the single ideal flame ball. And you can see that here, counterflow flame temperature distribution is blue line, and the flame ball here. And then ball-like frame is in between them. Now, since flame ball solution temperature distribution is proportional to the distance radius, right? Inversely radius, proportional to 1 divided by radius. So the temperature is in between them. So probably that what we observed is something in between two flame modes. That's what our current interpretation. Okay, this is summary. I think it's maybe over. Sorry. Oh, this is 1 hour. You see? Okay. Let's have second break. Before that, any questions? Oh, 2 questions.
Can you hear me?
Yes.
Okay. From the video you have showed us in the counterflow and the flame ball, does flame ball have some kind of surface tension effect? Because from what I see, maybe there is something about that, but anyone from the scientists or laboratories consider that?
Surface tension. at flame? I don't think so. Surface tension is you know, in the two-phase flow, right? Yeah. It is both gas phase.
Okay.
Next question.
Hi.
Hi.
When you put the equivalence ratio in the graphics, do you maintain the flow or you just change the flow?
In which figure?
In order to increase the equivalence ratio, you higher the flow or you maintain the flow and just concentrate or not the gas?
Okay. Flow meters are computer controlled. So we just give the total flow rate constant,
yes.
and then fuel concentration decrease slightly. But this means that oxidizer flow rate is slightly increased. Okay. But it doesn't matter. It's, you know, in the figure, experiment is conducted like this or slightly this. Whichever, it's the same result would be obtained.
Okay, thank you.
You're welcome.
In slide 26, what the scale of flame ball are we looking at?
In our experiment, it's like 5 millimeters to 1 centimeters.
Yeah. Okay.
What decides this I mean, what are the factors behind this radius? I mean, is it fuel specific or is it some operating condition that dictate the radius of flame ball?
Okay. In the governing equation, the value at the limit, I mean, radius would be almost 0. Or not 0, some certain value, but decreasing anyway. So it's controlled by parameters, fuel, Lewis number, equivalence ratio. So that's the laminar burning velocity for the deflagration wave. The radius is the governing equation. So with the decrease of the equivalence ratio, the radius of flame ball is decreasing down to the limit. And the scale at the limit, based on the realistic radiation terms or something, is like a couple of millimeters to 1 centimeters, depending on mixture, which is not exactly agreed because it's open question actually. The kinetics, no kinetics is validated in such lean condition. It's no way to, you know, validate, right?
We have a question from Facebook, okay, from Alper Yantas. What are your views about the effects of plasma-assisted ignition system and gliding arc combustion system on flame formation and propagation?
That's an excellent question. Actually, that question is answered in the Professor Zhu's lecture in Princeton last summer. I didn't touch anything about plasma-assisted combustion, but he extended the discussion up to this range, also including cool flame regime. So in addition to the such curve that I showed, that additional limit for the cool flame limit is appeared. And then again, he started discussing about the extension of the plasma-assisted condition. It's excellent lecture, so I recommend you to watch that video. I think it's available now. Thank you. Next question.
I have a question here. So we are trying to understand how flames are behaving, and I believe it's in hopes of better controlling the flame and keeping it alight. My question now, it comes from the experiment itself on microgravity, because you are using a plane and you are controlling the G-force on the plane. So what happens to the flame inside the engine while you are doing the experiment? So how can we actually use the microgravity to better control our flame in the engine?
Okay, I think it's a good question. Of course, there's a gravity in the engine, and I think it's gravity change rather than gravity change. I think some vibration, very strong turbulence that dominate. But still, the principle that we found in microgravity should exist there. But maybe it's not the decisive mechanism. Turbulence, other condition. But if we think about the limit mechanism, an engine is operated under the very high pressure condition, right? And then contains many burned mixture from the previous cycle, also easier conditions, which might be I think it's a condition of the sort of the radiative reabsorption occur in the engine. I think this effect is significant, maybe in the extreme condition, maybe not. But still, that flame obeys the principle. Of course, many other factors, right? Turbulence, curvature. But I think it's, in some days, eventually, we can explain everything happening in the engine. But engine is there. Many, many unknowns. But really interesting research target. Actually, I have been working in the engine project for 5 years in Japan. I didn't include this material. And for lean burn engine. So this is really interesting, new phenomena. Only within the imagination. But this experiment tells a lot. The fact is that beyond some value, engines stop working, right? What is decisive mechanism? That's a big question. And also we need to distinguish the ignition limit, maybe there's no that word. Ignition limit and also ignition, lean flammability limit, which is first. That's a big question, I think. Does it make sense?
Yeah, thank you.
You're welcome.
Enough.
Oh,
okay. My question was this. All of these images, I assume, are chemiluminescence. This is photons coming from a molecule that was created in a chemical reaction. These chemical reactions typically are not at the flame front. Could it possibly, and these chemical reactions are quite often temperature dependent, so as your flames are getting colder and colder, the luminescent reactions are getting less and less and less.
Actually, that even though it is very close to the limit, temperature is not that low. This temperature is a bit lower. And then we are using methane, which is which activation energy is very large. And observations were made by using the intensified image without any filters. But it's different maybe if you use like heptane, maybe cool flame would appear, which is maybe very, very interesting topic.
Thank you.
Thank you very much for making a good question. Any other? Okay. Oh.
For the flame balls, if you are able to control the motion, what could be the future applications?
Practical application flame ball?
Yeah, could be.
This is maybe not my topic. It is you that, if it is useful, maybe for astronaut, when it is cold, air conditioner doesn't work, maybe they can use flame balls in the space station. I don't know. Sorry, it's not serious answer.
Yeah.
Any other questions?
Okay, I would like to ask if the measured combustion temperature is equal the adiabatic temperature. Did you see this phenomena? T adiabatic equal combustion temperature.
You mean this figure?
Generally. In general, does you measure combustion temperature and calculate adiabatic temperature, and you find that they are equal in value? Usually, adiabatic temperature much lower than combustion temperature, yes?
Why?
Okay. You calculate adiabatic temperature, okay? Do you measure the combustion temperature of the fuel?
What do you mean by the combustion temperature? It is flame temperature?
The actual temperature of the combustion.
Okay.
Okay?
You mean in the burn gas?
The working temperature of the fuel. Okay. Did you find that in any case that T adiabatic equal the T combustion?
I think so. It depends. This is the topic of the part 3. The real temperature can be lower or equal or higher than the adiabatic room temperature if you change the condition of a flame. I think that's a really very interesting question, yes.
Okay. You also said that we have a special case where T of combustion is much higher than, as you say now, is much higher than the adiabatic temperature, yes? So this is because the fuel absorbs some of energy, and total energy will rise the temperature above the T adiabatic, okay? But it's also, we can call it T adiabatic, because you calculate under adiabatic condition in case of no heat loss. So you have adiabatic temperature at normal condition and adiabatic temperature at preheating, okay? Is it right?
Easiest example is that the frames mixture with Lewis number less than 1. Adiabatic temperature is not affected by the stretch, so you have the certain value. But under the certain flame stretch conditions, the temperature of flame is much higher than the adiabatic flame temperature. This is a typical example. It is already observed in any counterflow flame experiment. Make sense?
You ask?
Yes.
Please ask me again, the question again.
No. If you have the mixture which Lewis number is less than 1, then put this mixture under some certain appropriate stretch condition, frame stretch condition. The flame temperature is much higher than the adiabatic flame temperature. Such phenomena is often observed in like counterflow flame experiment. Also for the mixture, if you ignite mixture and then outwardly spherical flame kernel, before reaching its absolute asymptote value, the flame speed was higher, that as I showed you. In that case, flame temperature is higher. Maybe kernel temperature, reaction zone temperature is much higher than the adiabatic flame temperature because of the Lewis number effect.
Okay, thank you.
Thank you. No. Yes. But in most of the case, it's not the case for the engine condition. Why? Because in engine, the fuels with large molecules are used. So in that case, usually that Lewis number is much larger than 1.
Yeah, when you were discussing the stretch effect as well, you said that it is the temperature from the burnt region that will kind of preheat the mixture.
No, not preheat.
Not preheat, like it will kind of...
because of the flame stretch effect.
Okay.
Maybe my explanation was bad. But in counterflow geometry, flame is under the effect of flame stretch. And the mixture with Lewis number less than 1 can have the higher temperature than the adiabatic flame temperature of that mixture. Because adiabatic flame temperature is defined for the one-dimensional flame, which is free from stretch effect. So if you have like hydrogen engine, maybe it is under the strong effect. That's the reason why that very small kernel is rapidly expanding. Since this is the curvature effect, the Lyapunov effect, the frame temperature is higher than the asymptote value, which is the adiabatic frame speed. That's the mechanism of the frame stretch.
Okay, so the usual enthalpy of reaction that we calculate then, it just includes the formation enthalpies and the sensible enthalpies, and it will not give us the correct enthalpy of reaction then if we do not include the...
In what geometry?
Just in general combustion process. So when we try to find the enthalpy of reaction, we just look at the enthalpies of formation and the sensible enthalpies.
Okay, so what's the configuration of flame? Because my point was that the frame geometry is essential to discussion.
To introduce the stretch, right?
Yes. So it's frame, then this effect is not appear.
Sorry, which flame?
If it is flame,
okay,
only, this effect does not appear.
If you have the higher equivalence ratio, you said that it becomes a planar flame. For the higher, it's for the fuel ratio.
In what topic?
In one of the slides I saw, where
I think it's the
some slide, some limits were shown for the higher equivalence ratio.
I think it's not higher equivalence ratio. It's the larger radius. Okay, I see now. You mean in the? Oh, this is, I think it's number 1. Let me go back to number 1.
Yeah. With the red lines, you have shown some limits there. It's in the ending. Yeah.
I think here. Do you mean that? This figure?
No, you have shown the vertical lines where the equivalence ratio was plotted on the x-axis.
Okay.
Red lines, yeah.
You mean the boundary?
Yeah, boundary. Yeah.
Okay, sorry. This, right?
Yeah. So, so beyond that, is the flame is becoming flameless or something like this?
In which one?
Beyond that, you can say planar
central
propagating flames can exist. You have wrote some.
Okay. Actually, that I didn't use this figure for explanation because this is the H2O2 mixture. Yeah. And here is the domain where that frame ball can exist, and this is planar frame can exist. Okay. So for example, in these conditions, the mixture has both solution. So then this is the initial value problem. How you start the phenomena. If you ignite, maybe in the gravity field, maybe to deflagration, but microgravity depends on. So frame can sit either one of those solutions. And also, this figure does not include any stability. So it's difficult to tell. So close to, it makes sense because if you have deflagration wave here, and then if you go further, and then maybe frame goes there. That's what conceptually saying that we observed.
And what is the effect of the Smith number on this combustion characteristics? What is the effect of a Smith number?
Effect of?
Smith number. Smith number. Smith number. SCIMM.
Or Schmidt number.
Schmidt number, yeah.
Schmidt number, but no flow, right? Schmidt number, Lewis number. I think it's not decisive mechanism. Lewis number.
Yeah, you had discussed about the effect of Lewis number, but
because please remember that for the condition that stable flame ball is observed, there is no flow. Everywhere, no convection flow, almost no convection. Ideal flame balls just observed in still quiescent mixture. But in the counter flame case, of course, very, very weak convection.
Thanks.
Let me start from this for part 3. This is frames under extreme conditions. Initially, that flame quench and excess enthalpy combustion are revisited. And then those two topics would be connected to the mild combustion and microcombustion. Those are the two topics that we have been working on. The quenching diameter. It is of course, in some textbook, it is written for a certain fuel. Quenching diameter is blah, 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 2 centimeters, 3 millimeters, 2 millimeters. But essentially, it is same as the formability limit. The frame is under the concept of this one. I changed. Let me go back. Yes, this concept. Very simple. Frames under the heat loss. And the heat loss was radiative heat loss in case of formability limit, but in case of quenching diameter, it is just a heat transfer to the tube. Those two are same. Now let's visit the flame in tube again. The heat transfer is shown in the red arrows. So fresh mixture is coming in, and then here, the burn gas. And the burn gas heat up the tube wall, and then some are lost to the ambient, and some are returned to the ambient mixture through wall, because even if it's quartz, the thermal conductivity is like 2 orders higher than the gas mixture. So this means that balance, heat balance, the way a flame shoots, are totally different from ideal 1D frame, and also the frames with a certain loss. Some loss and gain again. And in the earliest work by Weinberg, he uses such Swiss roll geometry. And also Professor Roney from USC also worked by using the 2D and 3D Swiss roll for the power generation. The combination with the Swiss roll plus thermoelectric devices installed along the wall, and try to utilize the temperature difference between the two sides of the wall. And then my work is just a very simple Swiss roll. And actually this is the essential result of the excess enthalpy combustion. Please look at the temperature distribution of combustion. You can imagine it is in tube, or even you can imagine it is in the porous media. Of course, the geometry is different, but it is saying that in addition to the gas phase, you have the solid phase, which is another media of the heat transfer from the burned gas to the ambient mixture. So this means the frame is totally different thermal conditions compared with like free gas frame. And here you have the adiabatic frame temperature. And since wall temperature is lower than gas temperature, because heat is coming from gas to wall, But because of the large thermal conductivity, this wall temperature reversed. In the upstream region, the temperature of gas can be lower than wall temperature, which means that this is the typical condition of excess enthalpy combustion. So this means the flame is preheated. Then enthalpy balance. Chemical enthalpy is released in the reaction zone, and then temperature, sensible temperature is higher in the burn gas. But because of the heat feedback, the mixture is preheated like that, then gas phase temperature can be higher than the adiabatic flame temperature. It's different from the Lewis number effect stuff. That's what we discussed. It's the common situation in porous media combustion. And in tube, same. And this is some of the experimental work in early 90s. I think it's from 80 to 90 by the Japanese researcher, Professor Echigo. They use porous media. And from one side, they supply mixture. And then because of the heat of combustion, porous media is heated. And then heated area is propagating to the upstream gradually. So then finally heat up. And then change the direction of the flow. And then again, porous media temperature is like something like propagating. But during those modes, the local gas temperature can be much, much higher than the adiabatic flame temperature. So this is so-called the excess enthalpy combustion, which is very useful because temperature is higher than adiabatic flame temperature. Also, the flammability limit is much wider. I forgot the correct number, but the methane air mixtures at equivalence ratio, I think it's 0.01 or something, can be flammable in this device, which means, okay, flammability limit is just a value decided by the condition, not the flame property, just decided by the thermal conditions. We learn from the microgravity experiments, counterflow flame experiments, right? If we just put the radiation term into the governing equation, then it is readily predict all the flame behavior. Flame ball same, and here is same. So this means by using the concept of the excess enthalpy combustion, you can burn something with very low calorific value, very low quality fuel. And also, if you want, you can have much higher temperature than the adiabatic flame temperature. So this is a concept of the excess enthalpy combustion. So that's the reason that I have been working on the excess enthalpy combustion. Okay, for considering the efficiency of the combustion device, it is very useful to visit the exergy loss, availability loss during combustion. In one group in Japan, from the chemical engineering, they are trying to propose very nice idea to use all the exergy recirculation. So they propose the social system, which does not include any combustion, starting from the reformation. Okay, what is exergy? Exergy can be chemical, thermal, whatever. Then by using the exergy recirculation, it's like a heat pump. Then increase the use of the exergy, and then attain the optimum conditions. So this is the numerical experiment of the one input, one output system, combustion system, maybe. And as a function of inlet temperature, if you look at the loss of exergy of the outlet burned gas, then it has like a 30% value. So this means that when the chemical energy is converted into the thermal energy, For the most of the hydrocarbons, the 30% of the exergy is lost. The hydrogen case a bit smaller, but this situation can be changed if you increase the incoming temperature. The loss 30% would be up to 10. And when you operate the outlet temperature, then again, the loss is decreasing. So this means just bring the exergy level up before combustion, and then after chemical heat release, and then use it for something, for any output. And this leads to a very, at a glance, strange suggestion based on very simple thermodynamics. During a break, I have a very interesting discussion with where the, okay. This is, first, very basic thermodynamics first law. This is, thermodynamic first law efficiency, which is the, exergy divided by the input thermal energy or chemical energy, whatever. And most of the case, if you try to increase the efficiency of the devices, you're trying to increase the first law efficiency, which means that try to raise this bar in upward. But on the other hand, also that always we have the unknown loss of the exergy due to the irreversible process. But for the higher final efficiency, this bar should be upward. Then it is same if you try to increase this or if you decrease this loss. It's same. To show this very in straightforward manner, I will just tell you that one example which compares the combustion of the ideal adiabatic flame with the mode of excess enthalpy combustion. This shows the adiabatic combustion. This is the diagram of the temperature enthalpy curve for the 1 mole of methane. So you start combustion here, and then for the isobaric combustion, just combustion in 1 atmosphere. And then you have the adiabatic flame temperature here. And just assume, by using this burned gas, let's try to heat something, maybe in a furnace, up to the temperature 1100 K, this value. Then you can effectively utilize the energy from here to here. And then if you compute the 3 kinds of the efficiencies, the first one is the ratio of the utilized thermal energy to the heat generation. Second, ratio of the utilized exergy to the fuel exergy. And third one is ratio of the utilized exergy to the total exergy. And look at this curve. This one is here. So it is below 40%. So assume that if you heat something at the temperature 1100 K with the combustion starting from room temperature by using 1 mole of methane, then only 40% exergy was effectively used. On the other hand, if you employ the excess enthalpy combustion, here, excess enthalpy combustion, then after start of the preheating, the incoming exergy is increasing up to point D because of you just heat up by the burned gas. And then start isobaric combustion, and then burned gas reach the slightly higher temperature than the previous adiabatic flame temperature because of preheating. And then just assume same to heat something up to 1100 K here. And then you can utilize, of course, I think this is only attained by the ideal heat exchanger. Of course, it's not possible this is extreme case. But since it is preheated up to 1100 K, the energy from this point to this point can be all used to heat something. And then the ratio of exergy to exergy, utilized exergy to total exergy, becomes, I think it's more than 70%, which makes 30% larger value than the previous one. So don't burn room temperature fuel. Don't burn room temperature oxidizer. I think in industry, this is very common knowledge. But this is extreme case. So roughly 30% useful energy were used just by introducing this process. Okay, by this, we can make another, it's not experiment. How do you say it in English? It's experiment in your brain. Just, okay. Top figure shows adiabatic flame, which we deal at part 1 today. And second one we deal is a flame with certain heat loss, which lead to the discussion on flammability limit, quenching distance, whatever. And third one, of course, this distribution is somehow strange, but this is heat exchange and then chemical reaction, which is higher temperature than the adiabatic flame temperature. This mode can be reached, of course, porous media tube, also some radiation emitter from burned gas to the radiation receiver in the upstream. Or you can combine 2 frames or something like that. And is it not realistic? Do you know any example of such combustion is attained? Where is Paul? Okay, let me go on.
Here we have.
So in the last slide, you talked about preheating. And I said that the preheating effect could be captured by the first law. And that would be the sensible enthalpy that I couldn't really get complete sense of it. How do we capture the stretch effect in the first law of thermodynamics?
Now I'm not talking about anything about stretch rate.
Yeah. So now it makes sense. That's what I'm saying. So now you said preheating, and it can be captured by the first law of thermodynamics. But what I couldn't understand that how the increase in temperature because of stretch could be taken care of by the first law. How do I plug it into the first law?
Maybe he will talk about that later.
I think it's a different topic. So we can utilize both. But in this case, we need to consider anything about the stretch.
Yeah, but we had the stretch in the previous part.
Yes.
But like at the end of the day, it comes down to the first law.
I think you can superimpose 2 effects. But now for the discussion, we don't need discussion on the stretch. Maybe it's not convincing, but okay, at this stage.
Oh.
Okay. Please remember that 30% increase of the. Okay. Who is familiar with mild combustion? Okay. Very effective, right? Very effective, mild combustion. Yes. Yes. Okay. This is the one big project which started the early 90s and continued to the 2003-4. We call that high temperature air combustion technology because it is the air is preheated before combustion. Usually it is not good tactics because if you increase the air temperature, the NOx would be increasing. But just by accident, the young engineer found something very interesting in 1980, and now it's all widespread. Maybe I think it's similar experience, but I believe that it is from Japan, at least this. And what is the high cost? This is the concept. This is the oxygen concentration in fresh mixture. This is the temperature of the fresh mixture. And usually combustion occurs below like 400, 500 degrees C. Any combustion devices, like gas turbine, same, engine, same, after compression. And furnace, if you preheat up to like 1,000 degrees C, combustion is possible if you have like appropriate heat exchanger. But in this case, large amount of NOx, so it's useless. But once, if you mix the incoming chemical enthalpy, fuels, with a lot of burned gas inside of the furnace body, then you can avoid the very intense reaction zone, which is the source of the large NOx. So this means that oxygen concentration of the fresh mixture can be lower, lower, and then down to maybe typically like 3%. So assume that many, many exhaust gases remained, and just a small amount of fuel and appropriate amount of air is introduced, then such combustion will occur. How? So this is the typical concept. Now, we have the two like regenerator. It is a heat exchanger and fuel nozzles. And then during this side works as burner. This side works as a heat stage. Oops. So after some repetition, that air temperature is very high, like 1100 degrees C, because of heat exchange here, and then only 100 degrees C temperature increase by chemical reaction. And then this burned gas heat up this heat stage. And once this temperature is very high and high, and this temperature low and lower, then just switch directions of flow. And then same things happen. And then interesting is that after the heat exchange here, flame temperature distribution inside here is not uniform. Very strong function of the location. So before the exit temperature becomes higher, the direction should be switched. Then that you can attain something like that exhaust temperature below 200 degrees C. So which means all the chemical enthalpy coming into this system is effectively used to heat something, and no exhaust loss. This is exactly equivalent to the condition that I explained right now. And this stage, such type of the regenerator media is used. And then interesting is that under the high cost mode, actually that flame disappears. Of course, flame is there. If you really good at, if you look at that zone very carefully, or if you make the laser measurement, some of the radicals and blue reaction zone are observed, but not like the common combustion like that. This is soot formation. Why? Guess why? Anyone? Yes, twofold. One is that the fuel is injected very high speed, which makes the turbulent mixing very fast. So it's not premixed system, but rather because of the very fast mixing, it's like an ignition controlled field. So up to the findings of this mode of combustion, there's no fundamental work. Why? Because it's not premix system, it's not non-premix system. but it's really similar to the combustion in porous media. And then in this mode, actually the highest temperature is far below than the NOx generation. So it is used and widely applied to various things. And let me go back to this initial figure. Here, there's a one curve here. This means this curve, the author of this figure was thinking about the premix system. So he thought it was impossible to mix the premixture without reaction up to such high temperature. But nothing worried about that, because you can use the very high-speed jet like this condition. So this is the fuel jet in a very high temperature air, and if the speed of jet is slow, the flame is attached to here. So the very intense reaction zone occurs, which produces very large amount of NOx. But once you increase the speed, then the flames start to lift. And then here, mixing occurs. Actually, here also that low temperature reaction occurred. And then this is ignition control system. And since the environment temperature is very high, the flame never blows off. So very, very stable. So you don't mind about the location of oxygen supply and also the fuel supply. So it's like not uniform, but it's like a uniform reactor by attaining the condition that in the figures suggested. And then this technology has been applying to some of the realistic devices, and like big reformers, also thermal furnaces up to, I think this is an old number, but I think it's most of the furnace has drastically improved their efficiencies. And average of the more than 1,000 furnace to retrofit the old furnace is like 30%, which is roughly equal to the very simple estimation. No NOx, almost nothing. And the combustion noise disappeared because no flamelet. Very silent combustion. And also that temperature is much more closer to uniform temperature because no flame. So this means that you can have the very small side of the furnace body, which means you can decrease the size of the furnace. And what is the source of the very large furnace? Always it's just a surface, loss from surface. If you decrease the size of the furnace, proportional to the area of the surface of the furnace, the loss can be decreased. This effect is very drastic. So then you can have very high thermal efficiency. Oh, it's already 15 minutes. Okay. So far, okay, then microcombustion. Maybe I need to skip most of them. Okay, so far, we learned what? Flame limit is controlled by a certain heat loss. So flammability limit, quenching diameter is not a property of flame. It's just a condition-driven event. So this means you can control the flammability limit. If you introduce some of the heat generation heat recirculation, mass recirculation, then you can change the condition of combustion. Which means if you have a small system, but with something with excess enthalpy combustion, you can have small combustion, right? Size doesn't matter. So that's the primary motivation that I had in year 2000. After making a microgravity experiment, I learned, okay, flammability limit can be controlled. Then let's go to the microcombustion, because flame quenching, nothing. We can overcome. And then we started two projects. let me speed up because I have 10 minutes. Based on Swiss law, I have one project which uses this as a heater, which is replacing the electric heater. And another one is that just by accident we observed, trying to resemble the inside condition here, and then use this as a sort of chemical reactor, the two-folds. Maybe no need to repeat, excess enthalpy combustion can be attained, by this geometry. And then compare with the electric heater, we can have the large, I think it's very high efficiency is expected, because if you heat something by electricity, it is the case that if you need to control the heating temperature very precisely, it's common to use the electric heater in industry. But instead of that, if we use such body as a heater body, then, okay, this is primary energy. Just assume it is fossil fuel is used, and then electricity is below 40%, right? And then if you use the electric heater, you need to start from this value. But if you use the excess enthalpy combustion heater, and then you start from 100 because of heat recirculation, and then exhaust temperature is very low. So by the experimental fact, it can be down to like 15% or 10%, which means it's at least twice better than the electric heater. This is the initial idea. And then we developed the pump-top size combustion devices, which is with the just one temperature feedback control, which attains the temperature controllability within 1K, plus minus 1K. And we produced some devices from pump-top size to the coin size, all self-stabilized. And then based on that our collaborator industry tried to scale up like this size and use the 70 units into the furnace, and they now working on the products for the food processing industry, and which attains that 70% reduction of fuel consumption compared with the previous model, because it is hard to attain the energy saving in that space. It's really simple principle, because if you use a combustion for cooking or heating something, it's unavoidable to have the very high temperature burn gas. But in this case, the exhaust temperature is very low. And then given chemical enthalpy is all effectively used to heat something. But that's the reason that such drastic temperature decrease is attained. 10 minutes. Okay. During the development of such heater, we observed very strange phenomena. We visualized the inside of this visceral burner and found something very funny flame like this. Okay, let me explain what is this. This is what we call microflow reactor with a controlled temperature profile, which is just a quartz tube, $10. And heat from outside. The original motivation is just try to resemble the condition inside of the Swiss roll geometry, because it was hard to stabilize flame, because temperature, because of the heat of combustion, body itself is heated, and the temperature at center is higher than the peripheral part, of course. So the incoming mixture experience increasing temperature channel up to the center. So that's why it is very hard to stabilize flame, because flame is trying to flash back into the entrance. So for resemble this, just external heater, whatever, electric heater, burner, whatever, was attained, and then this diameter should be small, because for attaining the very small Nusselt number, so that the temperature of the flame is not fully controlled by the chemical enthalpy of the flame, rather than the given temperature distribution to simulate it. And then we have several flames, as you can very easily imagine, normal preheated premix flame, of course. And then this flame, which looks like very thick, like 2 centimeters, 3 centimeters. And in addition to that, we have at very, very low flow conditions, low velocity conditions, we have another very stable flame, which has very, very low burning velocity, if I say burning velocity. This flame is observed sort of below the mixture velocity at inlet is less than 2 or 3 centimeters over second. This is, what is this? Okay, 3 frame, normal frame. Okay, second frame here is actually that the ignition occur at the high temperature side. This is just auto-ignited, right? It's, of course, because temperature is high enough, so it's auto-ignite. So the flame kernel or ignition kernel is runs to the upstream, to here. And then, of course, temperature is low there because of large heat loss. This ignition failed, extinct. But again, the fresh mixture is coming in. The next mixture is just ignited at the downstream, right? It's common. But here, just stable flame. Why? Because there is a point that local flow rate and the flame burning at preheated premixture is balanced. But why? Here, because of the Spalding theory, after the certain heat loss, that stable solution disappeared. So that's why, but flame does not extinct because heated from outside. So ignition, extinction, repeat occurred. And at the very low speed, again, very, very funny frame, which is temperature increase is very low. Okay. Then my colleague, actually my Russian colleague, the Dr. Sergei Minev, has made some analysis of this situation. And then this is the experimental fact, 3 mode. And here is the same plane. The result was that stable solution here and another stable solution here. Here is another unstable solution, but flame doesn't care about this solution and just ignite, distinct, ignite, extinct. This is somehow analogous to the SCurve phenomena. Let's go back to SCurve phenomena. This is flame solution. This is cold solution. But imagine that if you have the third axis at initial temperature. So this means that if you have this layer twice, 2, 3, 4, 5, with increasing temperature, then so many S-curves with different lowest temperature can be formed here in 3D geometry. This is a case for this quartz tube. So in this branch, slightly elevated temperature, the solution branch appeared. So that's the frame that we observed there. Okay, what's the property of that frame? We measured their temperature. Actually, the difference of the temperature of flame with wall temperature. This value is typically 20 but with the decrease of the flow speed, this is asymptote to 0, but at a certain point it disappeared. Here it's temperature difference at reaction zone with wall temperature is 2 or 3 K. But below that, flame disappeared. Why? Because of the diffusion loss of the radicals. Because the flow speed there is very low. It's almost equivalent to the diffusion velocity. So the incoming enthalpy, but lost enthalpy by diffusion compete, and finally lost diffusion win, and then flame is extinct. Okay, this is what we call weak flame. Okay. 5 minutes, yeah? Okay. Okay, what is weak flame? flame with, if I can say, burning velocity is like 0.5 centimeters per second or 1 centimeters per second. Temperature, just above the wall temperature, or 2 or 3 K at the extreme case. But very small amount of chemical enthalpy is formed. But this flame is sitting on the branch of the ignition, right? Which means that this flame can be used to validate or to explore the ignition chemistry, right? Instead of the shock tube or RCM, we can utilize it, this flame. So the initial experiment was done by the methane, but we switched to the flames with low temperature chemistry. I think most of you are familiar with that, but I think it's on Wednesday. I think it's very excellent chemical, fuel characterization. So we have 3 reaction zones together for the weak flame condition. And then, let me skip. Very simple computation with the heat transfer term between wall and gas phase. 3 frames, 3 heat generation. And this is the CH, mole fraction. Not like, but something like peak, some increase. Compared with the wall temperature profile. Here, mainframe, some temperature increase. Here also, and here, very little, but some temperature increase. What are these reaction zones? By comparing the computation and also by sampling experiment, finally we found that this first very weak reaction is low temperature oxidation, producing the H2O2 and the CH2O here. And then here, it's intermediate reaction. Sometimes it is called blue flame, and sometimes it is called like partial oxidation, because here, the reaction up to CO is ongoing, not fully oxidized. And the third point, it is fully oxidized. So CO all consumed, and then have all the CO2. Which means that by this weak flame for the fuels with low temperature chemistry, we have the 3 reaction zones at one time. LTO, medium temperature, and final temperature. So let me skip. This is what I told you now. First reaction zone, second reaction zone, and here, CH2O is converted in HCO, and CO, but not fully oxidized. And third reaction zone, CO is fully converted in CO2. And this prediction is almost same as the measurement result. Of course, it's not perfect, but agreement was fair enough to explain the interpretation. Okay. Then this is the 3 weak frames here. I'm sorry. This is 3 weak frame here. But look at, for example, shock tube or RCM. You have 2-stage reaction, LTO and HTO. But in the reactor case, because of the very small amount of chemical enthalpy is coming in, and also that flame cannot make the thermal runaway partially because of the small chemical enthalpy, and also because of the temperature restriction by the external temperature distribution and also very small diameter. Here, usually that one reaction zone, those 2 reactions are combined because one thermal runaway occurs. But here we can have the separate reaction zone, blue flame and main flame. So this cool blue main flame. Okay, then we can utilize this one to check the difference of the fuel property, such as octane number, right? Then if we bring the PLF, the mixture of the normal heptane plus the isooctane, and then change the ratio, which is the definition of the octane number, right? And then we have, this is actually the N-heptane mixture, which has the 3 reaction zone, but with the increase of the octane number, isooctane fraction, up to 100% isooctane, the low temperature flame disappeared, and also location of blue flame and higher temperature shifts slightly to the higher temperature side, which tells that fuel property. So usually that ignition is observed in 0D situation, but this system enables that fuel property can be described by 1D system. So I think I can skip. Overall, experiment and computation agreed. And if we just collect the whole set of the experiment we have done, the locations of those multiple flames, and also that flames only with the high temperature reaction, the order of the octane number and then flame location can be aligned by this. So it's 5. I think it's practically same result using the vertical type reactor, trying to increase. And also this is the one that we try to push out the second and third flame because we want to measure the concentration of the species in only the cool flame. So the highest temperature of the two is limited to like this 700 K, and then this is only cool flame is attained here. And let me skip 1, 2. And then based on the sensitivity analysis, among the several paths of the LTO, we found that 2 paths are dominant in these conditions. One is for radical branching path, which leads to the aldehyde, and others are radical propagation paths, which pass through the cyclic ethyl to lead to alkenes. So then we decided to measure those species. Let me skip this. And then measure those stuff. Main measure species. We employed the Livermore mechanism for heptane KUCLS made in Japan, and also model field library. And then none of them can predict the species distribution. At this stage, we don't know the reliability of the experimental data, but we tried and repeat and repeat. So, and then this is the aldehydes and alkenes, also some different behaviors. And then finally, the branching ratio of the radical propagation branch, and then branching and propagation reactions, and then also no chemistry can predict at all. And then we work on different things, like since there is no limit, we can use this for the validation of very lean mixture, like equivalence ratio 0.3 or something. So we can test the reliability of chemistry in such conditions. Also, some laser diagnostics was made to check the methane reaction at very, very low temperature. I don't know if it is important or not. And also, soot formation and pH formation below the temperature 400 K. Of course, some reactions occur, but no data exists. So some measurements, CO, C2, H2, C2H6, C2H4, C2H2. And it is convenient because here's soot formation here, and here the one reaction occur, a very weak reaction occur. And then in this zone, we can observe the reaction of some of the C2 species, which is lead to the smaller pH, leading to C1 ring and up to the C4 ring or something like that. So in principle, if we can search these zones, we can check the validity of the chemistry in that temperature zone. Important thing is effect of radical quenching. We checked, and then well-known wall chemical effect mechanism published in, I think it's 2001, was significantly over predict the effect of radical quenching. This was confirmed by the experiment combined with 2D computation focusing on the measurement at the exit CO concentration as well. And also, this is the work by the group from U Tokyo. The same principle, give the very precise temperature distribution, make the laser measurement, and then they put the surface of the quartz, like stainless steel and quartz itself, and aluminum, very thin layer, at 120 nanometers, which doesn't change any thermal property. And then check the radical concentration very close to the wall. And then what they found was that the sticking coefficient is different, but believe that existing chemistry is suggested that sticking coefficient 1, which means the very, very large chemical wall effect. But in fact, the aluminum can be, 3 orders different, quartz 2 orders different, and stainless steel has some effect. So which means that the chemical wall effect is very small. And then it can be neglected in the condition that we have been working on. And this reactor is now commercialized to make as an test device of the fuel. And then so far that 2 devices are delivered to the industry, automobile companies in Japan. And my dream is here. We have small reactor here, and then check the fuel property before combustion in engine. So this is the fuel flexible vehicle, because that now the year of the fuel diversity. So you can use any fuel, but something like octane number property is very, very important to preserve the engine, also to attain the highest efficiency. Okay, sorry, 7 minutes passed. Okay, that's it. Thank you very much for listening. We don't have any time for making questions. Any questions? Very quick questions.
Okay. Thanks for this informative lecture. I just need more clarification regarding the excess enthalpy combustion. Based on the practical application of this process to combustors, it means it will require constant supply of this high energy air, let me say, or preheated air, which maybe in practical applications might be challenging in terms of trying to have the high efficiency. So how about the issue of exhaust gas recirculation? Couldn't that help?
Yes. That's an excellent question. Actually, if you just forget about the very practical difficulty. Mm-hmm. Recirculation process can be heat, mass. I only talk about that. But together with that, pressure is same. So this means that increasing the compression ratio is same. HCCI, same. But if you increase the compression ratio, you need to have another issue, right? Knocking. HCCI, why it's good? Of course, HCCI is good. But compared with the SI combustion, the auto-ignition has smaller exergy loss because there's no conduction process. Conduction loss eat up the exergy. So in this sense, premix combustion is not that good compared with the auto-ignition. So in every aspect of the combustion usage, we can try to consider how to increase the exergy level before combustion. Of course, other problems should be appeared. But this is one way of consideration, maybe not common. This is maybe my idea. I don't know it's useful or not, but I believe it might be useful. And then this explains the very highly efficient furnace, right? And also that for engine people, it is common that in 90s, up to late 90s, EGR is only used to decrease NOx. And use the very cold EGR, right? But modern engines utilize like hot EGR, exhaust valve, closed, timing, it's controlled, then try to actively use the remaining energy or mass or whatever. So I think its recirculation process with exergy would increase the combustion efficiency, I believe.
Thank you.
So, regarding mild combustion, the temperature threshold to go toward flameless combustion, how does it change with pressure as you increase the pressure?
Actually, there's no boundary, right?
Okay, yeah, I mean, but you have it's not a real boundary, but there is a temperature for which...
Okay, so regarding the mild combustion, the very nice review papers by the Italian group, like, and then they have some temperature of ignition temperature. They have some classification. That works very well.
I remember the paper, but it's most of the studies on mild combustion are atmospheric pressure. Yes. I'm wondering what happens as you increase the pressure, if to have a flameless combustion, which direction does it go in terms of temperature? Is it more likely at higher pressure or is less likely?
I think, okay, if you increase the pressure, mixing would be hard. So it's essential to have the well mixing before combustion. So in this sense, the higher pressure, it would be hard. But if you just overcome this difficulty, I think it's available.
Mixing. Yeah.
Yes.
Thanks for the very nice lecture. But I still with mild. Do you think there is a particular role of heat loss at walls in mild conditions, since the particular conditions mild, very homogeneous, and no high temperature, and still high temperature near the walls? I don't know. But
you're talking about
the heat loss at walls in mild combustion conditions. It's kind of different respect to standard combustion, since the reaction zone is also spread near the walls as well. Yeah, I think about small systems, because of course in the furnaces the heat loss effects are.
Okay, reaction can be close to wall or center of wall, whatever. But usually that they have like very nice thermal insulator. And outside of the thermal insulator, the temperature is like 40 degrees C or 50 degrees C or something like that. It's unavoidable because the thermal conductivity of the thermal insulator cannot be smaller than the air, that of air, right? So the temperature is anyway higher than the ambient. Even at such temperature level, the temperature difference from ambient times surface area is the primary source of the heat loss in the furnace. And it is difficult to eliminate. The most effective way is to have the smaller area of the wall, which means that compact furnace. Make sense?
Yeah. Hi. So I have a question. So you talked about the flame stability in counterflow flame and different burner. So do you think we can relate the flame stability in a counterflow flame to a spray burner, which is kind of a real application of real engines, to understand the stability of two-phase flame?
I think it's yes. And as you may know, that some researchers are working on the counterflow spray frame.
Okay.
The difficult part is that, the sprays often remain up to the reaction zone, and then sometimes, just pass through, which break the assumption of the counterflow. As a fundamental work, maybe it is okay, but if you try to utilize the information, fully utilize the information, you need to be very careful to comparison with the difference of the conditions. But I think it's very useful to make the counterflow spray combustion.
Thank you.